Hello, this is Walter Leite, and in this video I will show how to evaluate close fit of a structural equation model using fit indices. So I have here a model that is modified from an article by Trella and colleagues at 2014. And first I will fit this model to the data. So I will click here on calculate estimates. Okay, and these are the estimates. Now, before I can interpret any estimate, I need to look at model fit. So I'll click on view text. And the top results here show that the chi-square is 18.26, degrees of freedom of 3, a p-value of 0.004. So this model doesn't have exact fit. So it doesn't fit exactly to the data because the chi-square test shows that this model fits significantly worse than the saturated model. Now, we typically don't stop at exact fit and we look at close fit because the chi-square test is very sensitive to minor misspecifications, especially if the sample size is large. So you could have very small misspecifications, but with a large enough sample size, you don't get exact fit. So for close fit, we look at fit indices, and those are available if I click here on model fit. So the top part here is the chi-square test, which is about exact fit. And the first line is the chi-square that I just showed. The second line is the saturated model, which has perfect fit. And the third line is the independence model, which is the worst possible model, just saying that all variables are independent. Okay, so we'll skip this part and we'll go into fit indices. So Amos reports several fit indices. I recommend using the IFI, TLI, CFI, RMSEA, which is shown lower here, RMSEA, for evaluating model fit, because those have been shown in simulation studies to be independent of sample size. So they have been shown by several simulation studies to work well. They are not completely independent on model type, and they have to be used in conjunction. So I will look first at IFI, TLI, and CFI. And those, for the TLI and CFI, there is a well-known paper by Hu and Bentler, 1989, that recommends a cutoff of 0.95. Then there are subsequent papers that show that that cutoff is very conservative. So typically I use 0.9, but several editors would require more strict criteria of 0.95. So here the TLI and CFI, the TLI is 0.96, 4, and the CFI 0.89. And those indicate that the model has close fit. I mean, the TLI and CFI are looking at improvement in fit over the independence model here, and the CFI is the maximum is 1. The TLI can go a little bit above 1. So either with a more strict criteria of 0.95 or a more liberal criteria of 0.9, both TLI and CFI show that the model has close fit. Now, the IFI has to be studied less, and 0.9 is an acceptable criteria for IFI, and this is 0.89, so it also shows that there is close fit. The root mean squared error is a bit different because it is not comparing with the independent model, so it's an absolute fit index, and also it's different because the expected value if the model is correct is 0. So we want it to be as close to 0 as possible. And it has a known distribution, so there is a confidence interval and a p-value for it. So here, Amos is reporting that the root mean squared error of approximation, RMSEA, is 0.045. Again, going by the very famous article by Hu and Bentler, 1989, this should be less than 0.06. So here it's 0.045, which fits that criteria. A less conservative criteria would be 0.08. Now, a common significance test is to check whether the root mean squared error is significantly less than 0.05, and that is the p-value for that test is here. It's 0.63, so it shows that's not significant, like that is not different from 0.05. So this p-value shows that it's close fit. This test it's the only fit index that has a test. Also has confidence interval. So the confidence interval is between 0.026 and 0.065. So it includes 0.05, and that's evidence that there is close fit. Amos also reports information indices. The AIC archaic information criteria. Here, for example, BIC's Bayesian information criteria. Those are useful to compare different models, particularly if you don't have nested models. Now here we are not comparing different models, we're evaluating a single model, so these are not useful for that. So based on, this model, the conclusion here by looking at these fit indices, IFI, TLI, CFI, and root mean squared error of approximation is that this model has close fit, even though it does not have exact fit, as shown by a significant chi-square test. Now, if you wanted to modify the model, I mean, you could report a model that has close fit, but if you wanted to modify, obviously the best way to modify it is based on theory. Now, there are modification indices that Amos calculates, which is a specification search, like trying to see what change would decrease the chi-square. However, you have to use modification indices carefully because they are not based on theory, and they can suggest changes that don't make any sense theoretically, right? So it's saying here that for covariances, it's suggesting that if I add a correlation between each, which is the residual for adolescent behavioral problems, and education, the chi-square would decrease by 13.448. And the parameter change is what the expected value of that correlation would be. Now, and here for regression weights, if I add a direct path from education to adolescent behavior, my chi-square would decrease by 16.45, and this would be the expected value of that path, right? So if I wanted to modify those models, I could add those two suggested paths. But again, your theory should take precedence over modification indices.